The largest stone at Baalbek in Lebanon weighs over 800 tons, more than a fully loaded Boeing 747, yet it was lifted into place over 1,000 years before the first iron crane existed. The Baalbek Trilithon consists of 3 such stones side by side, totaling over 2,000 tons, among the heaviest objects ever moved by human labor. This was not an isolated feat. Across the ancient world, from Egypt to Greece to the Andes, builders faced the same challenge: how to lift massive stone with nothing but human strength and simple tools. The entire enterprise of ancient monumental architecture, the pyramids, temples, colossal statues that define entire civilizations, depended on solving this problem. The simplest answer, the ramp, is only part of the story. Ramps work, but they require staggering amounts of earth and labor, and they become impractical beyond a certain height. For a structure like a pyramid, a single ramp could require millions of tons of fill and a vast workforce. This forced builders to look for additional techniques. They combined levers, counterweights, pulleys, and eventually wooden cranes, all without iron gears or winches. But ramps could only go so high. What other methods did they develop? Ramps were the most straightforward solution. Instead of lifting a stone straight up, workers dragged it along a sloping surface, spreading the force over a longer distance so the same number of workers could move a heavier block. Archaeological evidence confirms ramps across continents. In Egypt, ramp remnants near pyramids and depictions of workers hauling statues on sledges up mud brick ramps. In Mesopotamia, ziggurats used similar approaches. In Mesoamerica, the stepped pyramids of Teotihuacan show signs of ramp-based construction, but ramps carried a hidden price. The first cost was material. A ramp reaching a pyramid 100 meters high required millions of tons of earth and stone, rivaling the monument itself. For the Great Pyramid of Giza, the ramp alone could contain nearly half the volume of the finished structure. That meant immense labor just to build the tool, and once the pyramid was finished, the ramp had to be dismantled. The second cost was height. A straight ramp needs a gentle slope, forcing it far outward. A zigzag ramp reduces the footprint but creates sharp turns where blocks had to be carefully maneuvered. As the structure rose, the ramp had to be extended, and for the uppermost courses the angle became steeper or the ramp impossibly long. So ramps could get stones partway up, but for final placement at great heights, builders needed another method. That is where the lever came in. The lever is one of the oldest simple machines, a long beam pivoted on a fulcrum. By pushing down on the long end, a worker could lift a multi-ton stone a few inches at the opposite end. The force multiplication is enormous. Archimedes, centuries later, famously boasted that given a lever long enough and a place to stand, he could move the world. But builders on the Nile knew the principle long before. We have direct visual evidence. In an Egyptian tomb painting from around 2000 BC, workers used long wooden poles to pry a massive stone block onto a wooden sledge. The poles slide under the stone. The fulcrum is a small stone or log, and a team leans their weight down to lift the block a handspan, just enough to slide a sledge beneath it. That same technique was used to inch stones into their final resting place on a monument. Once the block was close, workers could insert levers from the sides and nudge it millimeter by millimeter, aligning joints with astonishing accuracy. But the lever has a built-in limitation. It only raises the stone a short distance before the fulcrum needs to be reset. For continuous lifting, you need something that can climb with the load. That is where the next machine enters the picture. The next machine does not climb with the load the way a lever resets after each nudge. Instead, it uses a counterweight to make the load feel lighter from the start. The device is called a shadoof, and it is one of the oldest and most elegant examples of balancing forces in history. A shadoof is a long beam mounted on a pivot, with a bucket or cradle hanging from one end and a heavy counterweight, usually a stone or a basket of packed earth, fixed to the other. The operator lowers the bucket into a river or onto a stone, and the counterweight does more than half the work. When the operator pulls down on the counterweight side, the load rises almost effortlessly because the weight of the stone is mostly offset by the weight on the other side. The shadoof was used for irrigation across the ancient Near East, but the same principle was applied to lifting stone. In Roman reliefs, we see treadwheel cranes equipped with a large basket of stones hanging from the opposite side of the boom. That basket was a human adjustable counterweight, allowing the crew to balance the load before the treadwheel even began to turn. And in Han Dynasty China, builders used similar counterbalance systems to hoist heavy timbers and stone blocks into place. The shadoof itself did not lift the stone very high, perhaps a few feet, but it drastically reduced the force a single person had to apply. It was a force multiplier that did not need complex rope work, just a beam, a fulcrum, and a heavy rock on the opposite end. For the first time, a single worker could control a stone that would have required 10 people using brute strength alone. The pulley took force multiplication further. A fixed pulley only changes direction, pulling down instead of up, more convenient but no stronger. The real gain came from a movable pulley, which rises with the load and cuts the required force roughly in half because the rope bears part of the weight. String several together and you get a compound pulley or block and tackle, where each added sheave reduces effort further. The Greeks understood this principle by the 3rd century BC. Architects of Tarentum reportedly built a mechanical dove using pulleys, and by the Roman period compound pulley systems were standard on construction sites. A relief from the tomb of the Hatiri in Rome shows a massive block and tackle suspended from a timber tripod lifting a stone pediment, yet constraints limited the system. Natural fiber ropes, hemp or papyrus, could break under heavy loads, and wooden pulley blocks wore out quickly from friction. Rope also stretched, making precise vertical control difficult. Pulleys were never the whole answer. They required a sturdy frame and a power source like a treadwheel or teams of laborers. Still, the compound pulley let ancient builders multiply human strength by 4, 6, or even 8 times using nothing more than rope and grooved wheels, a concrete discovery that made the wooden cranes of the next generation possible. The solution was the wooden crane. By the 5th century BC, Greek reliefs show a simple hoisting device. A timber pole with a pulley at the top, guys ropes, and a rope wound around a drum turned by men on the ground. This earliest crane could lift a few hundred pounds. Soon came versions with 3 or 5 pulleys, all wood and rope, multiplying force several times. The real breakthrough was the treadwheel crane, a large wooden wheel often 16 feet in diameter with internal steps. 1 or 2 men walked inside, their body weight turning the axle to wind the lift rope. The wheel acted as a continuous lever and provided a steady counterbalance. A single man could lift several tons. Roman builders used these cranes extensively, raising column drums and architraves weighing 8 to 10 tons. The architect Vitruvius described them in detail, noting that larger cranes used a second wheel and multiple pulleys. These wooden cranes were portable, assembled on site, and lifted stones to great heights. But they had limits. The timber frame could only take so much stress. A crane designed for 10 tons could not handle 20. For the truly giant stones like those at Baalbek, builders needed more than a single machine. The treadwheel crane pushed the wooden crane design to its logical peak. Its geometry delivered remarkable mechanical advantage. A typical treadwheel measured 16 feet across, while the rope drum was barely a foot in diameter. That ratio gave roughly 16 to 1 advantage from the wheel radius alone. Men walked inside the wheel, pushing its full circumference, so their body weight acted as a continuous lever. A single worker weighing around 150 pounds could lift well over a ton. With 2 workers in the wheel, the load doubled. The crane itself was built entirely from timber, wooden pegs, and rope. No iron appeared in the lifting mechanism. The axle rested on wooden bearings greased with animal fat or tallow. The sturdy frame could be disassembled and moved between work sites. These cranes easily lifted stones weighing 8 to 10 tons, while larger versions with a second wheel reached 12 tons or more. Height was limited by rope length and the need to reposition the crane on scaffolding, but builders could hoist blocks over 100 feet above ground. The Roman architect Vitruvius detailed the design, and archaeological remains such as the crane at the Roman port of Arles confirm its construction. The treadwheel crane remained in use for over 1,000 years, powering the great cathedrals of medieval Europe. It was the peak of pre-industrial mechanical lift, a single machine that combined leverage, pulley, and human power to move the stones that defined ancient and medieval architecture. Lifting a multi-ton stone was only half the work. Once at the top, builders had to settle it flush against its neighbors, often within the width of a fingernail. They had no iron jacks or hydraulic rams. Instead, they used simple techniques that traded force for control. One method used wet sand. Builders set the stone on sandbags and slowly drained them. As the sand trickled away, the stone sank precisely. The Roman architect Vitruvius described this for leveling columns. For fine adjustments, workers used wooden wedges and levers. Tapping a wedge under one side tilted the stone a fraction. A lever in a crevice shifted it sideways. These adjustments could take days but required no metal and could be repeated. The Inca at Machu Picchu used dry fitting. They shaped each stone to fit neighbors before final placement, lifting it, marking high spots, lowering it again for carving. Each iteration brought the fit closer until the joint left no gap. Temporary wooden rails and greased tracks helped slide stones into position, with sandbags or wedges for the final millimeter. The result was stones locked together so tightly that they have survived earthquakes for centuries, all achieved with wood, rope, and careful hands. For long-distance transport, builders turned to the most abundant force. Water. The Nile was the great highway of ancient Egypt, and many pyramid blocks arrived at the construction site not by road but by barge. An Egyptian relief shows a colossal stone statue being towed, the water supporting its weight effortlessly. The principle is simple: water displaces weight. A stone that would crush any wooden sled becomes manageable cargo when buoyancy takes over, but water could do more than float a stone. It could lift one. Imagine a basin with a stone-laden barge floating inside. Builders would seal the basin, fill it with water to raise the barge, then open a sluice to lower it again, giving controlled vertical movement without any crane. The Canal of the Pharaohs used a primitive lock system that worked on this same idea. Even in the Roman world, engineers understood buoyancy. During the construction of the Colosseum, some massive stone elements may have been floated into position using temporary water channels and then lifted by the very water that carried them. And there was a less-known trick. Attaching empty pottery jars or wooden floats to a stone reduced its effective weight in water, allowing a smaller crew to lift it onto a higher course. Water was not a universal solution, but wherever it flowed, ancient builders turned it into a lifting force as reliable as any wooden crane. But even the most reliable water lift depended on ropes and timbers that were anything but reliable. In Egypt, rope makers twisted papyrus and flax into thick cables. In Rome, hemp imported from Spain and Gaul became standard. The process required even tension. A weak strand meant failure. Timber was chosen with equal care: oak for density, cedar for rot resistance, pine for straight grain. Every beam was inspected for cracks and insect damage. Yet natural ropes stretched under heavy loads, rotted in damp conditions, and frayed against rough stone. Timber could split without warning, especially if green or improperly seasoned. Builders compensated with carefully tied knots. The clove hitch secured a rope around a stone quickly. The constrictor knot gripped a pole with remarkable strength, and the square knot served general purposes. Each had to be perfect because a slip meant collapse. The quality of these materials set the ceiling on what could be lifted. A treadwheel crane was useless with a weak rope. A ramp was worthless if its framing broke. Builders built in redundancy, doubling ropes, enlarging timbers, inspecting after every shift. But the knowledge of which fiber, which tree, which knot could bear a given weight was rarely written down. It lived in the hands of rope makers and carpenters, passed from master to apprentice. That fragile human chain was as critical as any machine. That knowledge of rope and timber passed from master to apprentice, but a single rope maker could not build a pyramid. The real backbone of ancient lifting was the human system that coordinated thousands of workers. In Egypt, the workforce for a single pyramid was divided into specialized teams. Quarrymen cut the stone, haulers dragged it on sledges, lifters operated the ramps and levers, and masons set the final blocks. Each team had its own overseer, and each project had a chief architect who communicated between them. Ostraka found near the pyramids list daily rations, worker names, and tasks assigned to specific gangs. One well-known gang was called the Friends of Khufu, a name that suggests pride and competition. The workforce could number in the tens of thousands. Supply chains stretched for miles. Water, food, tools, and even the grease used to reduce friction on sledges had to be produced and transported from distant sources. All of this required a level of administration that rivaled any modern construction project. This administrative apparatus was as carefully designed as any ramp or lever. The bottleneck was never just the technology. It was the challenge of keeping thousands of people working in sync, day after day, for decades. Skills were passed down not through manuals but through generations of families or guilds. A mason learned from his father, and a lever operator learned from an uncle. This human chain of knowledge was as essential as any wooden beam or twisted rope. The greatest engineering achievement of the ancient world might have been not a single machine, but the social machine that made the machines work. All of this human machinery worked within a hard ceiling imposed by the materials themselves. Natural fiber rope, whether hemp, flax, or papyrus, has a breaking point. A typical Roman treadwheel crane could safely lift around 12 tons. That is impressive. It is enough to build a cathedral or a temple, but it is nowhere near the 100-ton stones at Baalbek or the nearly 60-ton obelisks that the Egyptians moved. To lift something that massive, you would need ropes as thick as a human torso, and the sheer weight of the rope itself would start to become a problem. The rope would stretch under load, and it would rot if left exposed to moisture. Wooden beams, no matter how carefully selected, would fatigue. A crane that worked for one season might develop dangerous cracks the next. These were not failures of imagination. They were failures of physics. There is evidence that some ancient projects were scaled back or abandoned because the lift simply became impossible with available materials. The medieval period saw a gradual solution: iron reinforcements, iron bands wrapped around wooden drums, iron axles in bearings, iron chains replacing rope for the most demanding lifts. This was not a rejection of ancient principles. It was an upgrade to the materials, allowing the same levers, pulleys, and counterweights to reach higher. The ancient builders had pushed wood and rope to their absolute limit. They had done everything that was possible without metal, and that limit becomes the next question. How do we know these methods actually worked beyond theory and speculation? Experimental archaeology has answered that question with full-scale replicas. The Thyra project built a Roman treadwheel crane using only wood, rope, and wooden pegs. In the early 2000s, it lifted a 10-ton stone block over 40 feet high. The crane worked, though the ropes creaked and the crew required careful coordination. A well-designed wooden crane without metal could handle loads that would impress a modern site. At the University of Colorado, researchers built a scale-model pyramid ramp from mud, brick, and wood. They tested how efficiently teams could drag a large stone up a slope. The angle mattered enormously. A shallow slope needed vast materials but kept the force within the capacity of about 50 people. Their work confirmed that long zigzag ramps for the Great Pyramid were physically plausible even if they consumed enormous earth and brick. The Nova series tried to build a small pyramid using only ancient tools and methods. The effort was messy, ropes broke, weight distribution was miscalculated. Yet they succeeded in moving and placing stones weighing several tons using ramps, levers, and wooden sledges. These experiments reveal hidden difficulties that no drawing captures. Rope stretches more than expected. Wood splits under repeated load. Human coordination is hard, but every major replication has concluded that the core techniques were real. We now have physical, repeatable evidence that ancient builders could lift multi-ton stones using only the tools described. The limits were real, but within those limits they achieved what seems impossible to us today. Experimental proof shows the techniques worked, but the deeper engine was not mechanical. It was cultural. Pharaohs and emperors justified immense effort as sacred or politically essential. In Egypt, the pyramid was a staircase to the heavens, a religious duty for the entire nation. In Rome, the Colosseum and Pantheon demonstrated imperial reach. Inca rulers required labor as a tax and a ritual obligation to the state and gods. The workforce was not uniformly enslaved. Egyptian pyramid builders left graffiti with titles like Friends of Khufu, suggesting skilled craftsmen with pride in their role. Roman records show organized guilds of masons and lifters. Incan teams worked in rotating units called meter with their own leaders. Coercion existed, but so did professional pride. The human cost was real. Wooden cranes could collapse, ropes could fail, and a fall from scaffolding meant loss of life. But builders invested in safety, staging, and careful organization because losing skilled workers threatened the project. They knew the danger and still chose to build. That changes how we see these structures. They are not just feats of physics, they are acts of collective will. The ramp, the lever, the treadwheel crane were tools. The real engine was a society that decided the task was worth its people, its resources, and its entire way of life. Without that motivation, the finest mechanical system would have sat idle. The Baalbek Trilithon in Lebanon consists of 3 stones. Each weighs around 800 tons and was lifted 7 meters off the ground. The stones fit together with gaps so tight you cannot slide a piece of paper between them. The leading hypothesis combines every method from earlier into one plan. It begins with a massive earth ramp, but the quarry sits close to the temple platform on uneven ground. There was no room for a long, gentle slope. Builders likely constructed a shorter, steeper ramp reinforced with timber and packed with stones. Instead of dragging the block up a gentle incline, they used multiple teams of workers and animals. Compound pulley systems at the top winched the block upward. Once the block reached platform level, it still needed to move into final position on top of a course of smaller stones. Archaeologists and engineers have reconstructed how a series of wooden treadwheel cranes on the platform itself lifted the block the remaining few meters. Teams on the ground coordinated with ropes and levers to guide it into place. For final adjustments, workers used wooden wedges and levers. They may have placed wet sandbags beneath the stone and slowly drained them to lower it millimeter by millimeter. Experimental archaeology has shown that scaling up from a 10-ton stone to 800 tons required banks of cranes working in synchronized lifts. The load was shared through a central boom or a massive timber frame. Coordination alone demanded hundreds of people, each with a specific role. They signaled through drum beats or shouted commands. Baalbek was not a mystery. It was a demonstration of applied physics, careful logistics, and the willingness to organize labor on a military scale. The Trilithon stands as a literal monument to the fact that when ramps, cranes, levers, pulleys, and human effort are combined, stones that would challenge a modern crawler crane can be lifted without a single piece of iron. But those principles did not vanish with the Roman Empire. They survived because they worked. Walk into a medieval cathedral under construction, and you would find the same wooden treadwheel crane that lifted stones for the Greeks and Romans. The designs had hardly changed, the same counterweights, the same pulleys, the same reliance on rope and timber that could be repaired with local materials. The treadwheel persisted for centuries because it was simple, reliable, and capable of lifting loads that would make a modern crane operator pause. You can still see them preserved in some European cathedrals, their massive hollow wheel waiting for workers to step inside and walk the load upward. Every modern construction crane uses counterweights, pulleys, and levers. The counterweight that balances the boom is a direct descendant of the shadoof. The block and tackle at the tip is a compound pulley system Archimedes would have recognized. Even the treadwheel survives in a different form. Remote construction projects in parts of Asia and Africa still use human-powered lifting devices that mimic its mechanical advantage because they need no fuel and can be built on site with local wood. The toolkit ancient builders invented was not replaced. It was only improved by stronger materials. Steel replaced wood, synthetic ropes replaced hemp, but the geometry of the lever and the mechanical advantage of the pulley never changed. What changed was the scale. The same forces that lifted the Trilithon now lift a 70-ton girder, but the people who stand at the controls still rely on the same elementary physics. The ancient builders built the foundation that every subsequent builder has stood on, and that foundation holds lessons for how we solve problems today. In disaster relief, where heavy machinery cannot reach, builders sometimes rediscover the same ancient methods. After the 2011 earthquake in Christchurch, New Zealand, workers used levers, cribbing, and ramps to stabilize and move debris when cranes could not access the narrow streets. The approach worked because it required no fuel and only what was at hand. When rebuilding historical structures, engineers often turn deliberately to traditional techniques. For the reconstruction of the Notre Dame spire, French carpenters used medieval lifting frames and manual rigging to hoist oak beams, not because they lacked modern tools, but because rope and wood placed less stress on the ancient stonework beneath. The deeper lesson is that the ancient builders did not rely on a single invention. They had a toolkit of simple machines and the patience to use them incrementally. They moved stones by inches, adjusting, testing, and repeating over weeks and months. That mindset of working with constraints rather than against them is often lost when we reach first for a motor or a hydraulic cylinder. Brute force consumes energy and can create waste. The ancient approach teaches us that the best solution depends on available materials, time, and environment, not on the most advanced hardware. Perhaps the most valuable insight is that complexity is not always an improvement. The ancients achieved staggering results with deceptively simple tools. The next time you face a problem that seems impossible, remember that the answer might lie not in more power, but in a smarter application of the basic forces you already have. That mindset was only possible because ancient builders understood that no single method was enough. The real breakthrough was not a single invention, but the intelligent combination of several simple ones. Consider the construction of a medieval cathedral like Amiens or Beauvais, where workers had to lift a spire stone weighing several tons to a height of more than 100 feet. They could not rely on a treadwheel crane alone because even that machine had limits, so they built a system. At the top of the scaffolding, they mounted a treadwheel which provided the raw pulling power. But the rope from the treadwheel did not go directly to the stone. Instead, it passed through a set of compound pulleys that multiplied the force several times over. And at the opposite end of the lifting beam, a counterweight made of several smaller stones balanced part of the load, reducing the strain on both the rope and the wooden frame. Each component by itself was a simple machine: a lever, a pulley, a counterbalance, but carefully combined, they created a system capable of lifting a stone that no single one could have budged. This synergy is often missed when we focus on the single impressive invention. The treadwheel crane gets the glory, but the real skill was in knowing how to integrate it with other tools to achieve what seemed impossible. That lesson, the power of compound simplicity, is what made ancient builders succeed where brute force alone would have failed. Ancient builders did not invent the iron crane. They invented something more enduring. The true genius was not any single invention, but the combination of simple principles, careful organization, and relentless persistence. The ramp, the lever, the pulley, the counterweight, the treadwheel, each was limited on its own, but together they formed systems that could lift almost any stone. That lesson remains relevant for modern problem solving, whether you are designing a crane or working with the tools you already have. Now, I would love to hear from you. Which ancient lifting method do you think was the most clever, and what modern machine still uses the same basic principle today? Subscribe to uncover the surprising engineering behind history's greatest structures and learn what we can still apply from the past.